We present Where2Act, from pixels to actions for articulated 3D objects. Imagine that you are presented with this cabinet, with an articulated door and drawer. What actions can you take on it? You may say that you can pull out the drawer by grasping the handle, close the door by pushing on the door surface, or open the door further by clamping the edge and pulling it out. For each of the possible actions, there are 3 parts: what, where, and how. The what part refers to the action type you can do, for example, pushing or pulling. The where part indicates the actionable regions over the shape geometry. In this example, one needs to grasp and pull at the drawer handle. The how part further proposes the agent side action direction to accomplish the interaction goal. In this case, we need to pull the drawer outward, not inward. We formulate a novel problem to study how robot agents can action over articulated 3D objects. Given this cabinet, we first define an action vocabulary for the what part. One may consider different action primitives, such as pushing, pulling, scratching. Then, for each action type, we train a neural network to predict a dense per pixel visual affordance heat map to answer the where question. Notice that for pushing, our network predicts that the flat surface pixels are in general pushable, except for the regions that are too close to handles. These pixels fail to support the action due to potential collisions between the gripper and the handle geometry. While for pulling, the high curvature regions are highlighted, with an interesting exception that the pixels at the intersection of door and drawer are rated low, due to collision failure if attempt. Finally, for the how question, we predict diverse sets of gripper action orientations at each actionable pixel. We also rate each action proposal with a success likelihood score, so that one can rank and pick among proposals. We design a novel network architecture to learn where to act and how to act, taking either a 2D image or a 3D partial scan as the input. We first leverage a state-of-the-art 2D UNet or 3D PointNet++ backbone to extract per pixel or per point features. Then, we firstly decode an actionability score at this pixel, using a simple MLP, answering the where question: is this action type good for this point? Next, a second decoder, formulated as a conditional generative model, proposes diverse gripper action directions for the how question. What actions can be taken? Finally, we train an action scoring module, which is also modeled as an MLP, to rate each action proposal with a score between 0 and 1. We perform our experiments using the large-scale PartNet mobility dataset, with a subset of 972 articulated objects over 15 categories, and a state-of-the-art simulation environment Sapien, to simulate realistic robot-object interactions. We hand-code task-specific short-term interaction trajectories, parameterized by the contact point and the gripper orientation, and collect simulated interactions to train our networks. Different from previous affordance learning works that require human annotation or demonstration, our system is trained in a fully self-supervised way. Results show that we successfully learn task-aware localized geometric features for visual actionable affordance, which is also generalizable to novel test shapes and even unknown object categories. On this slide, we show that our action proposal module can generate diverse gripper action orientations at actionable pixels. One can pick the most applicable ones given the robot kinematic configuration and environment constraints. Since our learned representations are localized, in cases that the domain gaps are not significant, we observe reasonable results directly testing our model over real-world data. Thank you for watching.